right. Yep. Welcome everyone to another gathering of the Community of Practice in Sustainable Concrete, proudly hosted by Smarty CRC. We are letting people in as they come, but without wasting anyone's time, let's get into it. I am Arun from Advanced Precast, and I'll be your host today. Before we start, in the spirit of reconciliation, we acknowledge the traditional custodians of country throughout Australia and their connections to land, sea, and community. We pay our respect to the elders past and present and extend the respect to all Aboriginal and Torres Strait Islander peoples today. It's great to have you here once again. These sessions are all about bringing together industry experts, researchers, and the wider concrete ecosystem to share ideas, discuss breakthroughs, and explore practical, meaningful approaches to sustainable concrete. And today we are talking about returned aggregate. We have an interesting session today, which is especially very relevant to what we do in precast. And for anyone who's using concrete, ready mix, civil, or even just pouring your driveway at home, think about it. You order concrete, you pour it, you finish the job, and what happens to the leftover concrete? You can't put it in the red bin, green bin, or yellow bin, or whatever the color your council suggests to. You can't drop it off at Coles or Woolies like batteries. You can't definitely donate it to Salvos. So what do we do with the waste concrete? That's exactly what we are unpacking today. Before we jump into it, a few housekeeping rules. The session is being recorded. We will share this with everyone who has registered for this event. If they could not make it in person today, there will be a link to the video presentations. We will really appreciate if you can keep the mic off while the presenters are presenting. We'll hear from each speaker in turn and then open the floors for questions. That being said, if you have a burning question during the talks, pop it into the chat box, raise your hands, or jump in once the presentations wrap up. We are fortunate to have two brilliant speakers, one from the industry and one from academia, offering perspectives from both sides of the fence. Without further ado, we'll go to the first speaker. Our first speaker is Vinod Rajayogan. Vinod Rajayogan completed his PhD in civil engineering from New South Wales in 2009 and is a member of the Institute of Concrete Technology, UK. He has been working with Holcim for over 16 years now, and currently he is the Regional Technical Manager for Western Australia. And he works in the system with concrete and support the concrete quarry and precast division of Western Australia for Holcim. Vinod, over to you. The floor is yours.
Hopefully I'm loud and clear. I'll just start off with my presentation.
Yeah.
Is that visible?
Yeah, all good.
Right.
All good, Vinod. Yeah.
And welcome everybody to the talk. I wanted to just take everybody through the journey of what Holcim in Perth has been venturing over the last 5 years. Probably would be an underestimate of what we have found as a challenge with concrete waste returns and where we are now and the work we've been doing with Curtin University. Within Holcim, we have had 3 pillars as part of our journey towards sustainability. One is around climate, which is focused on things like solar reflective index and light reflective index and how we are to achieve our net zero targets. Another pillar we have actually acknowledged as critical is circularity within our organizations and how we achieve that. And one of the key to this circularity is our products range called Agneo and EcoCycle, and I'll talk a little bit more about that in a few other slides. The third pillar for us is nature and people, which we focus on products related to water management systems, purification of water, bioreef systems, green walls, etc. And more can be provided at a later context. The problem we identified early on is return concrete for us is often overlooked to be a very small quantity within the industry. You get a little bit of concrete here and there returned off, 0.2 cubic meters left out, half a cubic meter left out, and often it just goes back to the tip. And this, while on a day-to-day basis looks like a small level, over time aggregates to be a significant amount of waste. It is acknowledged that this product can be 100% reused, but it's not often in mainstream. So we took on an understanding to look at not just CDM, but look at the return concrete waste that is generated within the Holcim operations in Perth, and see how we can maximize to at least use a minimum 10% of that in our concrete being recycled. We all know that our current economy is very linear, that we take, make, use, and dispose the waste, and that is no longer sustainable to where we are heading. And in order to be sustainable, we need to be circular. And circularity comes from first within our doorsteps before we go elsewhere. And that's what we took as a mantra when we started this journey, that let's recycle our waste we generate within our organization and our waste within our existing processes before we go elsewhere. With that, we have got a brand, EcoCycle. EcoCycle for us is any product within the concrete that has a minimum of 10% recycled content. To be simplistic world, concrete has 2,400 kilos of per meter cube, and we are talking about minimum 240 or 250 kilos of material being recycled. That will equate to at least 30% of coarse aggregate if we were talking on in terms of recycled concrete aggregates. We also wanted to go a step further and say that we will not claim for EcoCycle until this is third-party verified. And this is a process we are currently going through as part of this journey. What is the real problem we found? Over time, we found that our waste were generally being delivered to landfills. This is no different, I would say, in many industries, but this was very much misaligned with our strategic pillar on circularity. Often overlooked because it's so small quantities, but as it builds up, it was a challenge we took on to understand what can we do. Now, unlike crushed demolition waste, recycled return concrete often is not compacted. It may not be even cured adequately. And often there is a concern that this is different to C&D waste. So what did we start off? We started off first with understanding basic implementation of collating the fresh concrete waste and recording the information which is being returned back to our quarries and concrete plants. We said we need to start off with accurate information to understand what is actually happening and how much is being returned. If any of this can be reused within on the same day or returned into a place where this can be recycled. Designated areas were allocated within the concrete plants and in the quarries to collect this recycled waste. It was made sure this material is free of contaminants, especially fibers, to ensure that this could be used. The product was then crushed and screened. We have gone through different iterations over the process to crush and screen. We started off initially with just crushing and screening without any curing. We've then put in a process to cure it for a period of time before it's crushed and screened. We've then moved towards blending with virgin aggregates to reduce variation as well. And at the current market, over the timeline of let's say 5 years, we've now implemented 3 markets, 3 product streams we've actually been creating from this recycled material. 20 mil, 40 mil on the recycled sand is being made. In addition to that, we also monitor all the durability properties in line with the stain standards, and it's regularly assessed for Los Angeles abrasion, wet dry strength variation, ASR, weak particles. And in each production run, we also check for the shape and grading, particle density, and water absorption to ensure what and how can this product be used. Within our concrete plants, space is always scarce, but it was critical for us to delineate from virgin aggregates to allow for traceability. In at least 3 of our plants, we have isolated areas for a designated bin to be able to receive the recycled concrete is made with the right sizing to meet the market segments. In all cases, we've been assessing for the stain standards for 2758.1 and 1379. I would also acknowledge WA Main Roads, who have been fantastic in coming forward in acknowledging crushed concrete returns as a viable coarse aggregate within their standards as well for use in N-class concrete. And this is one of those partnerships with Main Roads as well, which has been very helpful for us to implement this within WA. Now, some of the key properties have been assessed, and I think Prabir from Curtin University will delve into it in detail. But we have assessed for the basic requirements within 27581 and have found that all these comply with exposure B1, B2, if not in many cases even exposure class C. While supplying within the concrete, it is often understood that slump and slump loss are critical. Strength is concerning if people are worried about loss in strength and drying shrinkage and infill finishability. Data has been found that over time, there has been minimal impact to slump loss strength, drying shrinkage, and infill finishability, provided the recycled content is about 10%. When I say 10%, I'm talking about 30% of coarse aggregate. This has been found to be the optimum point at which we find that there is no impact or negative impact to the concrete itself, that including no impact to cement penalty as well. Here's some just photos of in place. Now, over the period, we have, I would say, well over 20,000 cubic meters of concrete supplied with recycled material in Perth. However, this has been a journey where we have understood and evaluated what is the right thing to do at an operational level. Here's some performance parameters of trials done in 2020 when we started this process, where recycled aggregate was added on as a single product, and the results of shrinkage and strength performance at a binder count of 270 binder at that time. However, since then we moved away from adding the product as a standalone product. It is now provided as a blend. The blending appears to reduce the variability within the coarse aggregate. And currently we have extended the recycled concrete aggregates up to 40 MPa in applications where a customer requires these. Obviously, the challenge has been that we have limited ourselves to 10% of the total mass or 30% coarse aggregate, and the problem always is raised is, can we use more? And that's where Curtin comes in to understand whether the higher replacement and any other treatment methodologies can support us. However, with the ability to use that 30% replacement, we have embedded this process into our mainstream supply now into the business, and is across 3 plants where we constantly monitor for performance of concrete, and is quite widely accepted, or probably not even noticed in many cases. What stands out for us from EcoCycle is it's not just the recycling part, but it's also being endorsed by a third-party verifier, and currently Holcim is going through the third-party verification to ensure that the credibility of the recycling is warranted and is certified by an independent third party. And with that, I'll pass on to Prabir from Curtin Uni, who would talk about the treatment methodologies that have been implemented to increase the recycled material content.
Thank you so much, Vinod. That's a really good presentation and gives us a great overview of what this project is. And with that, I'll pass it to the second speaker, who is with us, Professor Prabir. Professor Prabir is a professor of civil engineering at Curtin University, Western Australia. His research expertise includes sustainable utilization of wastes and industrial byproduct materials in the development of low carbon and sustainable construction materials, like geopolymer concrete and concrete durability. His recent major research project include developments of ambient cured geopolymer concrete, nickel slag as a supplementary cementitious material, and fine aggregate, waste glass aggregate, recycled concrete aggregate, and mitigation of alkali aggregate reaction in concrete. He has authored over 200 technical papers, and his publications were cited over 18,000 times in Google Scholar with an H-index of 50. Professor Sarker is a chartered professional engineer and fellow of Engineers Australia. Over to you, Professor. Over to you. Yeah, and you have a few students who has also done some work on this. Yeah, and over to the team at Curtin University.
Yeah, thank you, Arun, for the introduction. I'm just looking at the presentation mode.
Looks good, Prabir.
Is it okay? Looks all right?
Yeah, it's perfect.
Okay, all right. Thank you, Arun, for the introduction. Thanks, Vinod, for the introduction of the material, that CRCA, where it comes from, and about the quantity and the current use of it at Holcim. So my presentation will include some of the results that we have studied in the lab using this returned concrete aggregate as a partial replacement of natural aggregate. And also we try to make some improvement of the aggregate by using carbonation, using the carbon dioxide, and also by using other method like a small percentage of SBR latex. So in this study at Curtin, we have Riyad Hassan is the PhD student in this project. Ajoy Kumar Shubha is the MPhil student in the project, and we have Vinod Fayez and myself. So I acknowledge the hard work of Riyad and Ajoy, who have done all the hard work in the lab. And we don't have Ajoy here today, but we have Riyad. So I may not be able to answer all the questions. Then I will pass it to Riyad. Probably Riyad will be able to help with those. So we also acknowledge the supports of SmartCrate, Holcim, Main Roads Australia to this study. So crushed return concrete aggregate. So Vinod has already presented that, so I will not spend much time in it. But the difference between crushed return concrete aggregate and conventional C&D waste aggregate is that this crushed return concrete aggregate, we use CRCA, is a very pure material. It doesn't have any impurity like a brick, or timber or tiles, those kind of things, glass, plastic that we can find in C&D waste aggregate. So it's a very pure material. The other difference is that this concrete is relatively young as compared to the C&D waste aggregate, C&D waste concrete aggregate. And this concrete, as we have seen, that it comes back to the plant and it is just dumped to the site, so it doesn't go through a proper compaction and just a normal curing, no special curing effort is employed. So these are the difference between the crushed return concrete aggregate and C&D waste aggregate. So that can make some difference in the properties of the aggregate and eventually some difference in the properties of the concrete made by using this. So this is the process that dumped concrete, crushed and made the aggregate. So why this CRCA? And as Vinod has mentioned, they are already using like 30%, 20-30% replacement of natural aggregate. So it contributes to reduction of waste, conservation of natural resources, saving virgin aggregate use. It can contribute savings of energy by less effort for crushing and transportation. So it promotes the circular economy. We'll look at some of the properties. Riyad and Ajoy has done more than what we have just presented here. We have just included some of the key parameters and test results here, but there are more that they have studied. So if we look at the grading, this purple line shows the grading of the 20 millimeter CRC aggregate. So we can see it's well within the requirement of the coarse aggregate grading. And important properties about particle density and water absorption. So CRCA 20 millimeter, it has a particle density was found like 2.58 as compared to 2.7, around 2.7 for natural aggregate. And what is the other important property is the water absorption. So CRCA has a higher water absorption of which is found about 4 to 5%. There is some comparison with C&D waste aggregates as well. So where it was found like up to 6%, 6.5% around that. Whereas for natural aggregate, it is very low, like 0.4%. So this is a well-known property that recycled concrete aggregate has a higher water absorption than natural aggregate. Some comparison of the strength using this CRCA. So here in the left side, we have the compressive strength, and in the right-hand side graphs, we have the comparison of the indirect splitting tensile strength. So in each of the graphs, we have two, the leftmost two bars are for control concrete using the natural aggregate 100%, and then we have 20%, 40%, up to 60% of CRCA, and in the right we have 20%, 40%, and 60% recycled C&D waste concrete aggregate. So if we, for example, if we look at a comparison, so it is about 50 MPa concrete for natural aggregate, and when we used 40% CRCA, well, we have got about 12% strength reduction. And for using 40% C&D waste aggregate, we got even more reduction in compressive strength. So with the increase of CRCA or C&D waste aggregate, in both cases, we can see a decrease in the compressive strength. That's normally what we can expect. And the indirect tensile strength, the trend followed the same trend as the compressive strength of concrete mixtures using either CRCA or recycled C&D waste aggregate. Some properties that can affect the durability of concrete. So here we have on the left hand side the volume of permeable voids of the same concretes with control 20% CRCA, 40% and 60% CRCA, and similarly 20 to 60% of recycled C&D waste aggregates. So what we see that there is an increase in the volume of permeable voids that we can expect due to the increased absorption of the recycled concrete aggregate. So with 20% CRCA, we can see the difference is very small, but with 40% CRCA, we have about from 10 to maybe 11.5, about 1.5% increase in the volume of permeable voids, and similar increase for 40% recycled C&D waste aggregate as well. But with 60%, we can see the increase in the VPA, volume of permeable voids is actually more for C&D waste compared to 60% CRCA. In the right hand side, we have the comparison of the rapid chloride penetration test according to the ASTM standard. So we have the recommendations of very low, moderate, and high RCPT values. So you can see control, then 20% CRCA and 40% CRCA, all within the moderate RCPT, but we can see an increasing trend of the RCPT with the increase of CRCA. Okay, and we can see similar trend in the concretes using recycled C&D waste as well, but from the comparison we can see the increase is even more for recycled C&D waste as compared to the CRCA aggregates. Here is a comparison of the sorptivity. So we see similar trend that we saw before. This is the control concrete, 40% CRCA and 40% C&D waste aggregate concrete. So we can see that with the CRCA, the performance is actually better than the 40% C&D waste aggregate concrete. Looking at the microstructure for natural aggregate CRCA and RCA, recycled C&D waste aggregate, just to see the interfacial transition zone, we know that that is the weakest point of concrete, and the difference that is well known is that for concrete using natural aggregate, we have one interfacial transition zone, whereas for any recycled aggregate, we can expect there are two ITZs. One is the old ITZ and one there is a new ITZ. So it is similar for both using CRCA and RCA. So that makes that contributes to some of the properties of concrete that we see, that there is a decline in some of the properties using whether CRCA or RCA is due to the effect on the ITZ. Okay, so from this we can summarize that yes, there is um, a compromise of some of the properties by using either CRCA or recycled C&D waste aggregate. So there is a room for improvement. If we want to increase the percentage of recycled aggregate, we can probably look at some sort of improvement by treatment of the aggregates. So here we have tried some of the ways, and one way was this by wet carbonation treatment. So we know that there may be um, some waste carbon dioxide available for some industrial process which can be recycled to this process. So Ojoy made this setup in the lab. It is a very small scale, but later he actually did make another setup which can treat a larger volume of aggregate. So this was the preliminary setup to see the effect of carbonation on the recycled aggregate in a very small scale, but then that was increased to a larger setup which could treat maybe 30-40 kg of recycled aggregate. So basically the carbon dioxide was flown through the water to diffuse it to make it dissolved with the water, and then react with the calcium hydroxide that is available in the recycled aggregate to form calcium carbonate, to fill some of the pores and improve the ITZ or the adhered mortar with the aggregate. So that's how this method can contribute to improvement of the recycled aggregate. So some of the results of using this liquid carbonation to recycled aggregates to this. So both CRCA and recycled aggregate from crushing of cylinders were used here. So we can see in the horizontal axis is the time of duration of the carbonation, so up to 100 minutes, and the vertical axis is on the left hand side is the change of pH in the aggregate, and the right hand side is the change of the electrical conductivity. So that shows the effect of the carbonation on the aggregate, that what is happening with this carbonation. So we can see with the increased duration of the carbonation, electrical conductivity increased and the pH decreased because the calcium hydroxide has reacted with to form calcite. So the pH has decreased. Excuse me. So this is a mixed proportion of using carbonated recycled aggregates for 1 hour carbonation and 2 hour carbonation for CRCA and for recycled aggregate from the crushed cylinder concrete. Okay. So we can see the effect on the deposition of calcium carbonate here. So the vertical axis on the left hand side is the calcium carbonate content, calcite content. Horizontal axis is the duration of carbonation, and the vertical axis is the on the right hand side is the captured carbon dioxide, so which can be related to the carbon dioxide sequestration. So you can see as the carbonation duration increased, the calcite content produced on the aggregate is increased in both types of recycled aggregate, and also the captured carbon dioxide is increased. Excuse me. Here is some more results presenting the calcium carbonate deposition on the aggregate. And this is the depth of the carbonation deposition, calcite deposition in the aggregate. So this vertical axis is the depth up to which the calcite could be found, and so we can see a comparison for 2 hours of carbonation of CRCA here in the left box, and in the right box it is the recycled aggregate concrete obtained from crushing of the cylinders. So we can see there is more carbonation happening in the CRCA. So the reason could be that because this concrete was just dumped without proper compaction and curing, so there was more unreacted calcium cement particles available, so which could contribute to calcium hydroxide and formation of calcite. So there was more pore filling effect of the carbonation in the CRCA as compared to the other recycled aggregate. So some more evidence of the calcite formation by using the thermogravimetric analysis. So for CRCA without any carbonation, CRCA with 1 hour carbonation, 2 hour carbonation, and the other type of recycled aggregate without any carbonation, 1 hour carbonation and 2 hour carbonation. So we can see the calcite is actually breaks down in this temperature zone about 700 to beyond about 700 degrees centigrade. So we can see this line, for example, at the bottom is for 2 hour CRCA. So more carbonation of the CRCA had higher calcite content. So higher calcite content means more improvement of the pore structure in the adhered mortar. And some of the physical properties, looking at the water absorption of CRCA without any carbonation, 1 hour carbonation and 2 hour carbonation. So you can see higher length of carbonation can improve the water absorption of the aggregate that is produced after carbonation. And the effect is similar in the other recycled aggregate as well. And the improvement in strength also was observed in the concrete made by using the aggregate after carbonation. So concrete made by CRCA without carbonation, concrete made using 1 hour carbonation and 2 hour carbonation, and these are the concretes made with other recycled aggregate with 1 hour and 2 hour carbonation. So you can see in both cases there was an improvement of the compressive strength by using the recycled aggregate which went through 1 hour or 2 hour carbonation. So the other method, is that Riyadh has been trying. This is still the tests are going on. So using SBR latex with the it's an emulsion to mix it with the recycled aggregate to get some improvement of the properties of recycled aggregate, improvement of the adhered mortar. So as SBR latex is a material which can show some bonding and can show some pore filling effect. So the bonding is important for concrete application, and that's why SBR latex was used. So Riyadh is using 2 different methods. One is using the SBR latex, adding the SBR latex to the aggregate before mixing it with the concrete, and so the other method is just adding the SBR latex when the concrete is been mixed together with the recycled aggregate. So these are some of the effects. So we can say this is the natural aggregate, CRCA aggregate, and SBR latex treated aggregate. So we can say without treatment, prior to the treatment, it had loose mortar, adhered mortar on it, and which has become a more compacted, more improved adhered mortar on the surface of the recycled aggregate. So this is a close view. If it is fully covered by the latex, then the aggregate can turn into this. So from this appearance, it can turn into this appearance. But this is a very controlled way of treatment. So we cannot expect all the aggregates to be covered like this, but this is just to show that what can happen to an aggregate if it actually gets coated fully by the latex. So the aggregate properties after the treatment. So we can see the CRCA, again particle density 2.58 without treatment, and with 1% SBR it improved to 2.61, and water absorption improved from 4.4% to 1.5%. So which is a great improvement that can be achieved by using the SBR latex uh, as a method of treatment. So Riyadh has been trying this 1%, 2%, and 3% SBR latex. That is the percentage of the weight of the cement, adding in two different ways, pre-mixed and during mixing. So these are the mixed proportions of concrete using 40% CRCA with 1%, 2%, 3% premix, and 1%, 2%, 3% SBR latex during the mixing of the concrete. So some of the results, okay, these are the workability and air content. It has some effect. More importantly, if we look at the effect on mechanical properties, so we can see this is the controlled concrete at 7 days and 28 days compressive strength, and this is CRCA 40 without any treatment, and this is the CRCA 40% with treated by 1% SBR before mixing with the concrete, pre-mixed. And this is 2%, this is 3%. So we can see with 1% there is some improvement if we compare the second bars and the third set of bars. We can see there is some improvement which is obtained by 1% SBR latex using as a premix in the aggregate. And when you compare with this same 40% SBR latex to the CRCA using during mixing. So we can still see some improvement in both pre-mixed and during mixing applications. So, but when the SBR latex is increased beyond 1%, so we can see a decline in the compressive strength. So we think that 1% may be a good percentage of SBR latex that can be tried to improve the aggregate properties. So some other properties related to durability, which is the VPV, we can see again some improvement here with 1%. Okay, this is without treatment, and this is with treatment. So improvement means the VPV has decreased compared to the second graph to the third graph. Okay. So this is again rapid chloride permeability. So without treatment and with treatment by 1% SBR latex, it showed some decrease in the RCPT and VPB. So further looking at why it can improve, so we have done some scanning electron microscopy and some EDS to find what is found in the pores. So SBL latex has the carbon content. So in some of the points, it was found that the carbon content was high, so which shows that the SBL latex actually penetrated into the adhered mortar, and that carbon can be found inside the mortar. And again, Riyadh has done this line scanning to see up to what depth this high content of carbon could be found, showing this is an indication that SBL latex has penetrated to that depth. So this is in micron from the surface of the aggregate inside. So we can see it can go to certain depth within the adhered mortar, which is an evidence that it can improve the properties, and that is the reason why we see some improvement in the compressive strength and the pore filling effect on eventually improving the volume of permeable void and RCPT. So these are briefly some of the results that we have got from the works of Ajoy and Riyadh. They have more results which was published in some journals and in the Concrete conference in Adelaide. So if you are interested, you can find it there, or we'll be happy to send it to you if anybody is interested to look, find out more about it. So that's all. Thank you.
Thank you for the fantastic and the detailed presentation, Professor Prabir. I think you covered all the technical information really well. And with that, we can open the floor for questions. There's any audience members, they have any burning questions, feel free to type it in, or put your hands up, raise your hand and ask away. But while they were thinking around the questions, I have a few questions ready to go. So for both of you, one question that I'd like to know is, so what are the main barriers you see for the widespread adoption of returned concrete aggregate, like in commercial mixers? Like, is there a technical risk? The way I see it, Prabir has addressed most of the technical risks, and is that a cost element, or is that a customer client expectation, or is there regulatory limits? And especially Holcim, how are you addressing those challenges?
Yeah, so probably I'll answer saying that the primary barrier was initially that this whether the licensing agreements to accept return concrete waste into your premises was to be resolved, and that had to be worked through. Then the other challenge often is in a quarry, mainstream crushing aggregates is the mainstream process, right? And in that you're introducing recycled material, that's a change in process and a change in acceptance within the quarry to actually crush recycled concrete. You know, if you are looking at a C&D recycler, they're often there. That's their mainstream role, to actually crush return concrete or the C&D waste. But for a quarry supplier, virgin aggregates and premium aggregates are the mainstream roles, and often recycled concrete is a barrier purely because it's a distraction to the quarry. But this was taken on as saying, yes, this is not a distraction because the pile of waste was just building up. So we took on to campaign crushing at the quarry in every second month to do a large run, and then we'll shut it off, and then we'll go back to our premium aggregate production. And that's how we overcome that over the period. But it requires both, not just it required commitment from both the ground level, people, staff to want to do this, at the same time as support from the management as well. And I would say both happened. The other thing is, once you make this product, you didn't want to shut it off and shut on off every time, because you wanted to have a constant stream of recycled aggregates being made and consumed by the concrete plant. So we found that, you know, using about 30% of recycled material in our blends up to 40 MPI was acceptable, and some precast, sorry, not precast, footpath contractors onboarding who would regularly use this product at that percentage and accept that use. Dowsing would be one of them in WA who are quite open into using recycled material in concrete. And that allowed us to actually manage that stream of constant flow of material coming in and going out. Because what you don't want is you make this product and you can't use it, or vice versa, you have a demand for the product and you can't make it fast enough. And this balancing act had to be happen. So we actually identified 3 plants where they would actually go through, and this constant stream. Obviously, we were not ambitious beyond the 30%, purely because we were not having any other treatment methodologies as listed in this project to be done. But this is just through the existing crushing and screening process itself. Probably what we did also is we blended with our virgin aggregates using crushing and screening process. That's allowed us to reduce some of the adhered water in the system and allowed to reduce the variability in the aggregate as well.
Very good. Thank you for the answer, Vinod. And there's a question. There's a raise of hand from Shafuddin Ahmad. Do you have a question?
Yes. Great. Thank you, Vinod and Professor Prabir. I just want to ask you with reference to decarbonizing infrastructure. There is it's critical to tackle climate change. I want to know whether in this field measurements or field, whether Holcim, whether you people have done measurements. What is measured carbon in infrastructure when compared to control, and how much we reduced by using this sustainable concrete. That's the first question. And with reference to measure, whether, and the second question is with reference to washing of aggregates. We are talking of recycle. And are we washing the aggregate? That's the question. Second, and with reference to region wise, I'm speaking from Canberra, and the climate goes sub-zero, and so whether recycle aggregates that as Vinod has presented his results, his some site photos, whether it can be used, how far can be used to Canberra environment. And so these are so I think these are the potential questions.
I can talk from Holcim. From our point of view, we are working through a process to be able to report on the EPDs for recycled concrete aggregates as one of our existing third-party verification. We're working through that as well. And once we do that, we will be able to at least publish for the existing standard crushing and screening and use of the recycled concrete aggregate as is, to understand the carbon impact it has on the concrete itself. So that process that is in process at the minute, and once it's been completed, we'll be able to share that in our EPD itself for the concrete incorporating recycled aggregates, what the carbon impact has been. With regards to washing, we don't wash the aggregates at this stage in any process at all. It is just crushed and screened, dry crushed and screened at the minute at the quarry itself, and hence why I think we've limited to what has been achieved with the 30% replacement in the blends in coarse aggregate. And then with regards to the other process, I'll leave it to Prabir to answer.
Yeah, thank you, Vinod, for confirming. Regarding the washing, we also did not wash the aggregate. We used it as it is in all these tests. So without washing, so as it is, and it had some fines content with it. So, and also as we mentioned that there was adhered mortar, and that is common to all recycled aggregates.
Yeah, and probably adding to the question on Canberra, I think similar to WI, I think every state is on a journey in Holcim to understand how we can bring circularity within our organization and in various shapes and forms. And I think it'd be worth reaching out to the organization within those local regions to understand what is being done. My understanding is, at least in every capital state, we are looking at this recycling circularity being implemented as a mainstream process within our organization to ensure this can be offered in the market, whether that's through C&D or through return concrete waste, depending on the market segment we are operating in.
Thank you for that, Vinod. You had a follow-up question asking what's happening in Victoria. Yeah, I am based in, and then you answered it even before I asked. There's a question from Philip in the chat. The question is, what proportion of coarse aggregates could be replaced with recycled concrete if returns were 100% utilized? can all the returned concrete be used in 20% to 30% blends in lower risk uses like footpaths if this was taken up commonly?
I think that is what we have been able to demonstrate, that when I say 100% utilized, it is utilized across, say, every ton of rock coming back is used up in 3 cubic meters of concrete roughly. To give you a perspective how it is being utilized at about 30% replacement rate at the minute. The number 30% works out to be around 300 kilos or roughly 250 to 300 kilos, depending on the coarse aggregate, which is what we have been promoting as a minimum 10% of the total mass of concrete as our branding for EcoCycle. And that has been accepted in markets, not just in footpaths, but probably even into slightly structural elements as well, up to 32 MPa, because as a blend, the product meets even exposure class C. We are watching shrinkage and other performance parameters through that as well, and finding that there's no impact at this stage. But once we go beyond the 30% blend, I think there is an impact to performance, and therefore we have limited to this position at this stage.
Yeah. Thank you, Vinod. Another question from Subra Marji. Thanks for the presentation, Vinod and Prabir. Thoroughly enjoyed the presentation. Just curious if the CRCA was treated with any agent before they were introduced in concrete, or they were used as is in concrete.
Yeah, thank you, Shubhra. Yeah, there was we have different mixtures in the results that we have presented. So there was control mix, which is only natural aggregate. Then we had CRCA without any treatment, as it is, that how we received it from Holcim. And then in some mixtures we treated it by carbonation and SBL latex, and we used it. So we have used CRCA without any treatment in the first part of the work.
And within Holcim, at the moment, the supply has been with no treatment, in just a standard effective crushing and screening process and process control, proper control of process within the quarrying, crushing, screening process itself.
So as I understand, no new admixtures being used before we do the crushing. All right. Okay.
No.
Yeah. Thank you for that. And there's a question from Zoe from Adbury. Zoe from Adbury. Do you have life cycle impacts of introducing carbonation treatments and SBR?
We haven't gone to that stage yet. So we are basically looking at the basic properties, how it can improve. So that is the first step. So we haven't done the life cycle or the environmental impact calculations yet. Yeah.
But expectation for Holcim would be to have EPDs of this, I would assume.
That is correct. If a process is implemented with one of these treatment methodologies, then an EPD will be always be backed up with an EPD. So I think when this project started off, it was initially to understand what is the boundaries where we sit and what can be done to improve the boundaries. 2 technologies were obviously implemented. One was carbonation and one was SBR. Purely to allow for flexibility on the ground to understand what the maximization is. And I think once one of these processes are embraced within the organization, then an EPD will be looked at. But at this stage, I think we were the research is coming to the conclusion probably another 6 months, and then we will look into whether this has a commercial benefit.
That makes sense. Yeah. Professor Wood, your hand's up.
Yes, thank you very much, both Vinod and Prabir, for the excellent presentation. My question is to Vinod, actually, on the practical aspect. Firstly, the crushed returned recycled concrete aggregates. Are they supplied as a graded aggregates, or they supply as different maximum size? That's the first part of the question. The second part is whether they need to be stored separately from virgin aggregates and introduced separately during the batching stage.
Yeah, so we went through a few iterations, Wood, when we initially started this project. We initially started off single size 20 mil, single size 14, single size 10, and we found that bin space in concrete plants is very scarce and it is not always viable. We then progressively have moved towards blending with virgin aggregates in the crushing process itself, and not at the plant. So we create a 20 single blend. When I say blend, it's a 20 single size aggregate with 30% recycled content and 70% virgin aggregates. We do the same with 14 mil graded aggregate, which is a 14 mil graded with 30% recycled and 70% virgin aggregates. And we also do -5 mil separate. So 3 sizes has been made. Now, in introduction into the concrete, it is depending on the market segment we have. If the market is a heavily footpath market we are working on, we use a 14 mil graded material as a single product introduced through the concrete plant with a separate bin. But if the market is, say, we're looking at 40 MPa panel mixes, we use a 20 mil single-sized product, which is a slower quantity. And in non-critical applications like blinding and all, we've been using the recycled sand as well. So we've tried different combinations to suit different applications, just to make sure that you don't end up with one waste being created from another waste, and there is a balance of use of all the products being made. But we find the 14 graded product works the most because it is a single product added within the batching process, and most plants only have one bin pair available. So we try to mix and match these. So this is one of the things we found is the supply and demand of the concrete requirement to the waste coming in had to be also matched. Otherwise, you end up with an imbalance of excess waste being brought into the quarry, or a demand for the recycled concrete being available, but there's not enough waste aggregates to create this. So we have been over time trying to balance this act over time.
Thank you. Can I ask a follow-up question, please?
Yes.
Go for it. Yeah.
When many years ago, I guess, when CSIRO looked at the use of conventional recycled concrete aggregates, I think they found that if you start replacing the coarse aggregate by greater than 30%, you may have a problem with the elastic properties. Just wondering whether that is part of the consideration, especially you're saying that you're using grade 32 and now you're using for grade 40 as well, is it?
We have trialed in 40, yes. But I think in typical applications up to 32 MPa, and we have trialed in 40, but the quantity is limited to 30%.
30%. So you're not, I mean, if you were to look for a higher percentage,
then we would need to look at
looking at the elastic properties.
Yeah. I think from a we were also worried about cement impact as well, and we found that at 30%, 25 to 30% was about the optimum quantity where no impact to carbon was observed immediately from an increased cement content as well. So therefore, that probably drove the need for limiting ourselves at this stage until further data was available as where it trended. So I think we have not explored beyond that 30%, I would say, in any case. And if in many cases it's limited to 25%, that works out to be roughly 250 kilos in a whole cubic meter of concrete, rough numbers. And that seems to be the case. And I take point on higher quantities will have an impact on elasticity and other properties which needs to be explored as well.
Yeah. Thank you, Vinod.
Thank you, Vinod. And if you have time for one last question, Shafuddin, again, the results were shown the use of CRCA in community paths, the footpaths, and in what other critical structural elements CRCA has been used in the field to this date?
I would say anywhere 20-25 MPa has been requested. It has been used. Slab on ground has been tested on footings, but I think the market segment, as you said, coming to 32 and 40 MPa, it becomes critical. So therefore, it's been in consultation with customers. But if you're looking at 20-25 MPa, almost every market segment has been touched on, which is predominantly residential footings and slabs.
I think from the commercial point of view, the slab on ground and the residential market is huge for a business case, I would assume.
Yeah.
I think that's all we have time for. Thank you so much for both the presenters. You did, and thanks for taking all the questions. It's a really good conversation we had, and sharing your thoughts and around this evolving industry. And all the best for the rest of the research, Prabir and his team at Curtin University for adapting it to the construction industry. Is definitely not an easy task for industry like ours. Or like some famous person said, the journey of 1,000 miles begins with a single step. And I think it's a Chinese proverb, but I might be wrong though. For any follow-up questions or collaborations, please reach out to SmartGrid CRC. We'll make sure your messages get through to the right people, and you'll hear from them. This is it from us today, and thank you for being a great community, and enjoy the rest of your day. Thank you.